Hello everyone, welcome to the course Nature and Properties of Materials, and this course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. I'm your TA Alka Jangir from IIT Kanpur. So in week 5 we'll talk about composite materials. So firstly we'll go through some sample assignment question, then we'll go through some lecture notes. These will help you in solving your assignments. So first question is, these questions are related to composites. So first question is, what is reinforcement in grey cast iron? So as you know, grey cast iron, steel, these act as composites. So what is reinforcement phase in these? Your options are cementite flakes or graphite flakes, graphite nodules or graphite spheroids. Answer will be graphite flakes. So in case of grey cast iron, they get their name grey because of their appearance grey due to graphite flakes that are present. So this is the microstructure of grey cast iron. In this grey part, this is graphite flakes. So in cast iron and steel, graphite and Fe3C work as reinforcement in a metallic matrix of ferrite or pearlite. So both are composite like structures. For grey cast iron, graphite is in flake form, while in steel, cementite is present as reinforcement. In case of other cast irons, graphite can form nodules, spheroids as well. Next question is, the continuous phase of a composite material is known as its blank. Your options are dispersed phase, reinforcement phase, matrix phase or fiber phase. So your answer will be, so continuous phase will be matrix phase. So this is what your composite looks like. So these are the fibers that act as reinforcement in this matrix which is continuous. So composite is made of two phases, matrix and reinforcement. So composite material contain mostly two phases, matrix and dispersed phase, which is not continuous. The matrix phase is continuous, which tends to bind the fibers together. It also protects them from damage and is used to transmit the load. Next question is, which of the following materials are common for whiskers? Options are graphite, silicon carbide, glass boron, steel tungsten or polymers and ceramics. Answer will be graphite and silicon carbide. So whiskers are one of the phases that are present in fiber reinforced composites. In case of whiskers, they are thin single crystals having an extremely large length to diameter ratio. Due to their small size, they have high crystalline perfection, and fibers are polycrystalline materials of small diameters, whereas spires have large diameters. So the common materials are graphite, silicon nitride, aluminum oxide, etc. and glass, polymers and boron, they fall under the category of fibers. Steel, tungsten and molybdenum, these metals are commonly used as wires. Next question is, in the Hall-Page model, hardness increases with a reduction in grain size because grain boundaries. Your options are act as source of dislocations or aid dislocation motion, or act as barriers to dislocation motion, or act as sinks for the dislocations. Answer will be In case of Hall page model, where as we keep on decreasing grain size, its hardness increases. So this one states that dislocations, they act as barriers to dislocation motion. These grain boundaries, they act as barriers. So a fine grain material, one that has small grains, is harder and stronger than a coarse grained, and due to a greater total grain boundary area to restrict dislocation motion, and grain boundaries also act as source and sinks of dislocation, but that is not the reason for hardness enhancement in metals. So this is your polycrystalline material. In this, you keep on reducing this grain size, then hardness keep on increasing, and these grain boundaries, they act as a barrier to the dislocation motion. Next question is, the below figure depicts the structure of blank composite materials. Your options are continuous, aligned, laminate, or dispersion strengthened. So in this case, this is example of laminate structure. And a laminar composite is a subcategory type of structural composite with a varying orientation for each layer. So with different layers, you have different orientation, which gives it higher strength. And these composite materials are used for their high strength. So in various directions, you can find that certain layer will be aligned in that direction and opposite to that direction. So it gives in all direction, it gives you high strength. Next question is, which of the following is the correct size range of dispersoids in micrometers in dispersion strengthened composites? Your options are 0.0001 and 0.0009, or 0.01 to 0.1 micrometer, or 0.1 to 1, or 2 to 2.7 micrometer. So answer will be 0.01 to 0.1. So this is the size range for dispersoids that are found in dispersion strengthened composites. So dispersoids in composites, they vary in size from 0.01 to 0.1 micrometer, and they are very small. Their size is an important factor for mechanical properties. Fine size dispersoids provide better properties. Next question is, which of the following is not a characteristic trait of composite materials? Options are high strength, toughness, modulus, lightweight, easy to assemble, or sensitive to temperature change. So answer will be last one. The composites are not sensitive to temperature change. So composites, they, in case of this reinforcement phase, generally provides a composite with more strength, stiffness and toughness due to the crack bridging. And the composite materials have great mechanical properties, corrosion resistance, and they are easy to assemble, and they are light in weight in case of fiber composites. So they aren't very sensitive to thermal shocks and temperature changes. However, they are more expensive than conventional materials. Next is, what type of material is often used in creation of soft actuators for soft robotics? Options are shape memory alloys, carbon fiber, nylon, or aluminum. So answer will be shape memory alloys. So shape memory alloys, they work great as actuators for soft robotics. Example is nitinol, And these shared memory alloys, they convert thermal energy into mechanical energy, making them desirable for making actuators. Next question is, chain polymerization mechanism may occur due to, options are cationic, anionic, only due to free radical and cationic mechanism, or all of the given options. So answer will be all of the given options. So free radical polymerization is a type of chain growth polymerization along with anionic, cationic and coordination polymerization. So free radical polymerization is a polymerizing approach by which successive addition of free radicals take place to form a polymer unit. Last question is, which of the following may alter the mechanical properties of reinforced? So your options are constituent properties, fiber length, fiber orientation, or all of the mentioned. Answer will be all of the mentioned. So all these three, constituent properties, fiber length, fiber orientation, etc., they affect the overall property of reinforced composites. And from this graph as well, we can see as you keep on increasing fiber length, so you see that the relative property such as modulus, strength, impact, they keep on increasing, but the processability keep on reducing. So it becomes harder to produce these composites. Now we'll go through some lecture notes. Firstly, what are composites? So these are natural or artificial mixtures of two or more distinct phases or constituents, and these mixtures may consist of metals, polymers or ceramics. The primary engineering goal is to achieve a better balance of properties from the combination of materials. So these are various composites that I used in a aircraft. So depending on the temperature temperature or pressure it has to withstand, so according to that these composites are chosen according to their strength and other properties. Next up in history also we have a lot of use of composites in Indus civilization, which was around 3000 BC. Straw reinforced bricks were used for making homes, and around 100 BC steel composites were formed by the repeated folding of a steel bar back on itself, and around 1800 AD during industrial revolution concrete and cast iron was being used. Then in modern composites we see that around 1950 to present we use fiber reinforced composites. Next, in nature also some composites are found, such as these exist throughout the nature, almost all natural materials. Some of the examples include wood. So in this case you have lignin matrix and hemicellulose bound in a spiral form. In case of bone, you find that you have organic fibers plus inorganic crystals, and you have water and also fats. And 35% of bone consists of organic collagen protein fibers with small rod like hydroxyapatite crystals, and this is the inner structure of wood. Next, also cast iron and steel, they are also composite structures. So in cast iron and steel, graphite and Fe3C work as reinforcement in a metallic matrix. So both are composite like structures. So as you can see, this matrix it is softer, and this graphite flakes, they have higher strength, so it acts as a composite. Next up we have classification of composites. So these are mainly classified into three composites: particle reinforced, fiber reinforced and structural composites. Particle reinforced can be classified into two classes: large particle and dispersion strengthened particle reinforced composites. So in case of structural, you have laminates and also sandwich structures. In case of laminates, there are various layers by changing their orientation, and in case of sandwich structures, some material is sandwiched between other material plates. First off, we have large particle composites. First off, we have large particle composites. Examples include concrete, which is composed of cement, which is matrix, and then sand and gravel. They act as particulates, and the particulate phase is harder and stiffer than the matrix. And reinforcing particles, they tend to restrain the movement of the matrix phase in the vicinity of each particle. The matrix transfers the fraction of the applied load to the particles, and there is improvement in mechanical behavior depending on the strong bonding at the matrix particle interface. And in case of concrete, you can see it is made from cement plus sand, stones and water. Next is dispersion strengthened composites. So particles are normally much smaller. This is size of your reinforcements. So with diameter between 10 to 100 nanometer, and the strengthening occurs on the atomic or molecular level, and the matrix bears the major portion of an applied load, while these small dispersed particles, they hinder the motion of dislocations. Thus plastic deformation is restricted such that yield and tensile strengths, they as well as hardness improves. Some of the examples include SAP, also known as sintered aluminum powder, which is flakes of aluminum coated with aluminum, which are dispersed within an aluminum metal matrix. So here the strengthening mechanism is shown. So this is your dispersoid, which has a diameter less than 100 nanometer, which has higher strength. So it has its own strain field around it in matrix. So as the dislocation keeps moving, so when it reaches near it, then this dislocation is locked. So that's why it can't move further, and there is dislocation pile up forming here. So this will lead to enhancement in its strength and tensile strength, also hardness of this material. Next is fiber reinforced composites, in which you have fiber phase as reinforcement. So on the basis of diameter and character, fiber phase can be grouped into three structures. So first is you have whiskers, which are very thin single crystals that have an extremely large length upon diameter ratio but have the form of fiber. These are flow free. They have very less defects because they are very small in size, and thus they are extremely high strength materials. But these are very expensive, and these include graphite, silicon carbide, silicon nitride and aluminum oxide, etc. Next up you have fibers. So these are the material that has at least length upon diameter ratio equal to 10:1. So either polycrystalline or amorphous, but generally polymer and ceramic are used as fibers. Next you have wires, which have relatively large diameters, and typical materials include steel, molybdenum and tungsten. So as you see in tires as well, sometimes metal wires are used to increase the stiffness. And this is how your fiber reinforced composite looks like. Next you have fiber reinforced composites having matrix phase. So the role of matrix in composites includes binding fiber together, protect the individual fibers from damage by the external environment, act as a medium to transmit and distribute externally applied stress to fibers, and it also serves as a barrier to the crack propagation. So your matrix is what it is softer, so it doesn't propagate crack very fast as seen in brittle materials. Next you have role of fibers in composite, which include it enhances stiffness, it also enhances strength, and it provides crack bridging. So and also it enhances thermal resistance. So crack bridging is, if your crack is moving through the matrix, then your fiber will deflect the crack. So it provides that type of crack bridging. Next up you have requirements of composites. So the matrix material should be ductile, and elastic modulus of fiber should be much higher than that of the matrix, and there should be adequate bonding between the matrix and fibers. Next you have stress strain curve for composites. So firstly you have a softer matrix which has lower elastic modulus as well as higher ductility and lower tensile strength, and also you have a your reinforcement having higher strength which acts as brittle material. So your fiber or dispersoid, they have higher Young's modulus, and also it is brittle. Now your composite shows properties in between both of these. So as shown here, it has a modulus in between these, lying in between, and you have ductility in between these, and also UTS lying in between these. So this is how your material, your composite will fail. Next up you have the volume and weight fractions. So in case of fiber or any dispersoid, some dispersion phase, so here F is for fiber, so it can be any reinforcement. So if VF, this is capital VF, VM, VB and VC are the volumes of fiber, matrix, voids and composite. Then these are the various relations. So firstly we define volume fractions. So fiber fraction will be volume of fiber divided by volume of entire composite. Similarly, matrix, volume of matrix divided by volume of composite. And fraction of void, it will be volume of void divided by volume of composite. Now all these fractions combined will be 1, and if you add all of these volumes, these will give you volume of composite. And in terms of weight, so for weight fraction you have to divide weight of fiber to the weight of composite, and void won't be having weight, so we won't be considering voids here, and weight of matrix divided by weight of composite. Next the addition of these weights will be 1, and weight fractions will be 1, and weight addition will be equals to composite weight. Therefore rho c times volume of composite equals to rho f volume of composite, volume of fiber, plus rho m times Vm. So rho is your density. So here you are just converting this formula, Wc equals to Wf plus Wm. So you can write weight in terms of density and volume. So this formula you will be getting, and the composite density. So here we know that in this volume can be written in volume fraction. So rho c Vc you will take in this side. So Vf upon Vc we already know it is small vf, and similarly it's small Vm. So this will be the relation. Next up, there are two types in which you can apply load to a composite. So one way is longitudinal. So the fiber direction you apply load, or they can be transverse direction. So in 90 degree to the fiber direction you can apply load. So these are two methods. First method is longitudinal modulus. So in this case we find out what will be the modulus in this case. So when you apply load in this direction, in fiber direction, so in this case the tensile load is acting along the fiber direction, and assuming perfect bonding between fibers and matrix, you will be getting strain of fiber equals to strain of matrix equals to strain of entire composite. So here all these three are equal, and these are longitudinal strains in fibers, matrix and composite respectively. And the tensile load PC in composite, it applied on the composite lamina, is shared by the fiber and matrix. So PC will be equals to PF plus PM. So load you can write in terms of stress. So as you know, sigma is equals to P upon A. So P will be sigma times A. So P sigma A equals to sigma F times AF plus sigma M times AM. Now in this equation, you take AC to this side, then AF upon AC, AM upon AC you will be getting as multiples. So as you know that area of composite will be equals to your area of fiber plus area of matrix. So in this case you can write it in terms of volume, keeping length constant. So here you can write your elastic modulus as elastic modulus of composite equals to elastic modulus of fiber times volume fraction of fiber plus elastic modulus of matrix times volume fraction of matrix. Next up you have transverse modulus. In this case you are applying your load at 90 degree angle to the fiber direction. So the tensile load is acting normally in the fiber direction. So here you can see that your load is in this direction. So in normal direction you will be considering the cross sectional area. So for fiber and matrix both it is equal. So stress is equal for sigma F, sigma M and sigma C. And the strain or deformation of the entire composite it can be given as strain for the composite is equals to strain in fiber times the volume fraction of fiber plus strain in matrix times the volume fraction of matrix. So this can be rewritten using Hooke's law as, now Hooke's law in this case you know that your sigma will be equals to strain times your elastic modulus. So E can be equals to sigma upon E. So you just put these values here for strain and you will be finding this equation. Now we know sigma F equal to sigma M equal to sigma C. So this will become 1 upon EC equals to VF upon capital EF plus VM upon capital EM. Here EC transverse will be equals to EF EM divided by EF VM plus EM VF. Next up you have metal matrix composite. So now we'll be talking about, based on matrix, you divide your composites in 3 types: metal matrix, polymer matrix or ceramic matrix. So based on material that is used in making matrix. So first, in case of metal matrix composite, your matrix will be made of ductile metals, which are usually aluminum, magnesium, titanium, copper, etc. And fiber can be made of carbon, silicon carbide, boron or aluminum oxide, etc. And advantages over PMC. So in case of polymer matrix composites, compared to them, you have here higher operating temperatures, and these are non-flammable. So as you know, polymers have low operating temperatures because they tend to soften, and also they are flammable because of organic component, and these are also greater resistant to degradation by organic fluids. But one demerit they have, that these are costlier than PMCs. And these are various properties of MMCs reinforced with continuous and aligned fibers. The applications of metal matrix composites. So in this case you can use these to make tank armors, golf clubs, space shuttle frames and antenna boom for the Hubble Space Telescope, which uses graphite fibers in 6061 aluminum, which is aluminum alloy. And then you have polymer matrix composites. In this case you have glass fiber reinforced polymer composites. So this is one of the type. Other type is, next we'll talk about carbon fiber reinforced polymer. So in this case your reinforcement is glass fibers. Matrix will be made of plastic. So it is most often epoxy or polyester resin. And next reinforcement is glass fiber or E-class, having diameter 3 to 20 micrometer, and typically 55% of silica, 16% calcium oxide, 15% of alumina, 10% of beryllia and 4% of magnesia. These are added as glass, and it is easily drawn into high strength fibers from the molten state. The limitation is service temperature, which is up to only 200 degrees Celsius, because above this polymer matrix starts to deteriorate. And applications are in automotive and marine bodies, plastic pipes, storage containers and industrial floorings. And for glass fiber reinforced polymers, you have tensile modulus and as 45 in longitudinal direction, and in transverse direction it is 12 GPa, and tensile strength is 1020, and it is 40 in transverse direction. Next up you have carbon fiber reinforced polymers. In this case you have matrix as polymer resin, and fibers are made of carbon, and carbon is have high performance fiber material because it has highest specific modulus. So in terms of when you divide your modulus with density, so you will be getting highest value for carbon. And the specific strength of all reinforcing fiber materials and it retains same at elevated temperature. And at room temperature it is not affected by moisture or a wide variety of solvents, acids and bases. And fiber diameters normally range between 4 to 10 micrometer, and applications are in carbon fiber wheel, Boeing 787 Dreamliner, which is nearly 50% frame of CFRP, and mountain cycle bicycle frame and frame, seats, racket, etc. They also use this composite. Its tensile modulus is 145 in longitudinal direction and 10 in transverse direction, and its tensile strength is 1240 MPa in longitudinal direction and 40 in transverse direction. Next up we have aramid fiber reinforced polymers, AFRP composites. So trade name of most common aramid fiber is Kevlar and Nomex, and these are chemically, this group of materials is known as polyparaphenylene terephthalamide, and it is known for its toughness, impact resistance and resistance to creep and fatigue failure. It has strong covalent bond axially, so in this axis it has covalent bonding, while in this direction strong covalent bond in axial and weak hydrogen bond in transverse direction, and it has a negative coefficient of expansion due to presence of kinks, and it is UV sensitive, so if it is left in ultraviolet rays, so it starts to degrade. And this Kevlar, Nomex, they are used in making bulletproof vests and armors, in ballistic products, also used in sporting goods and making ropes and missile cases, replacement for asbestos in automotive brake and clutch linings and gaskets. Next we have ceramic matrix composites. So ceramics are highly brittle in nature, and also they have low fracture toughness. In general, the fracture toughness of ceramics are 1 to 5 megapascal square root meter, and while for metal alloys it is between 20 to 90. And by using ceramic metal matrix composites, you can get fracture toughness can be increased to lie in the range of 6 to 20, and the crack initiation, it normally occurs within matrix phase, whereas crack propagation is hindered by the particles, fibers or whiskers, so they try to deflect the crack, leading to enhancement in impact strength. And these exhibit improved high temperature creep behavior and resistance to thermal shock. This is the brake disc of Ferrari race car, which is made of carbon fiber reinforced in silicon carbide matrix. Next we have cermets. So cermet is made of ceramic and metal. So cermet, in this case your composite of ceramic particles which are strong and brittle in a metal matrix, which is soft and ductile, and it has higher toughness and wear resistance than traditional materials. And for instance, tungsten carbide or titanium carbide ceramic is embedded in a matrix of metals such as cobalt and nickel, and only about 10 to 15% metal volume. They are used for cutting tools for hardened steels and electrical components such as resistors and vacuum tubes in valves, etc. Next up we have carbon-carbon composite. So in this case, both reinforcement and matrix are made of carbon, and these are expensive, and these have high modulus of elasticity up to 200 GPa, and strength even retained at around 2000 degrees Celsius. And it has low density 1830 kg per meter cube, and it has very high thermal conductivity 1000 watt per meter Kelvin. It has low coefficient of friction in fiber direction, and it also has high abrasion resistance. And the applications consist of missile con, B-2 bomber aircrafts, wing leading edge of the space shuttle. Next up we have laminated composites. So a laminate is constructed by stacking a number of laminae. So with changing the orientation of these layers, it can be of 4 types. So first is unidirectional laminate. So in this case, your fiber orientation angles are the same in all laminates, such as theta equals to 0 degree. So you won't be changing the angle. Second, you have angle ply laminate. In this case, you have fiber orientation angles in alternate layers are theta minus theta, theta minus theta, where theta equals to 0 degree or 90 degree. Cross angle ply is in this case, it's shown here. And cross ply laminate, here you change direction by 90 degree. So fiber orientation angles in alternate layers are 0 degree, 90 degree, 0 degree, 90 degree. Next you have symmetric laminate. So in this case you have identical ply in material, thickness and fiber orientation angle at an equal distance about the center line. So you will be having theta z equals to theta minus z, where z is the distance from the mid plane to the of the laminate. Next you have sandwich panels. So it consists of two strong and stiff sheet faces that are separated by a core material or structure. So it combines relatively high strengths and stiffness with low densities, and outer sheet is made of either aluminum alloy, fiber reinforced plastics, titanium, steel or plywood. Core material is made of rigid polymeric foams, example phenolics, epoxy, polyurethanes, and it can be either wood such as balsa wood, and in case of honeycomb you can have hexagonal shells. Sandwich panels, these provide low water absorption, good anti-corrosion properties and good thermal insulated capacity. So in between you can put some insulating material, so it will lead to provide good insulation properties. Next we have hybrid composites. So two or more different kinds of fibers in a single matrix. So for example, carbon fibers are strong and relatively stiff and provide low density reinforcement, but these are expensive. And when we talk about glass fibers, these are inexpensive and they lack the stiffness of carbon. And the glass carbon hybrid is stronger and tougher, and it has higher impact resistance. The fiber may all be aligned and intimately mixed with one another, or laminae may be constructed. Some of the applications include baseball bats, ice skates, etc. Now there are 5 techniques to manufacture composites. First one is hand layup technique. In this case, this is the technique. Here you have a mold, then you have applied some gel coating to easily separate your product. So gel coat is applied to open mold to avoid the sticking of polymer to the surface. This reinforcement is placed in the mold, and this base resin mixed with a catalyst, which makes it hard with time, is applied by pouring and brushing. So it is applied, and this is your reinforcement. It is also rolled down. Now layup is made by building layer upon layer to obtain the desired thickness. So you can, such as here this layer is made, again you can make one more layer depending on what size you require. For an epoxy based system, the normal curing time at room temperature is 24 to 48 hours, and this method is mainly suitable for thermosetting polymer based composites. Advantage of this method is that it has low cost tools that are used, and it is versatile. Disadvantage is that it is time consuming, inconsistent, and it is easy formation of air bubbles and disorientation of fibers is possible. Next you have spray layup technique. So it is very similar to previous one. Here you just are using a spray gun. So it is extension of hand layup method, and a spray gun is used to spray pressurized resin and reinforcement, which is in the form of chopped fibers. Matrix material and reinforcement may be sprayed simultaneously or separately. Some of the advantages of this method is continuous process, and it is any material can be used as mold, and error can be corrected by respraying. The disadvantage is it has inconsistency, it has no control of fiber orientation, and easily only one side is finished, and it is an environmental unfriendly technique. So in this case this is very similar. So here you have release gel applied, then polymer gel, and the reinforcement is applied using this spray gun. Next up you have pultrusion. So in this case it is made using pull and extrusion. So this is two techniques combined. So here you have automated process for the continuous manufacturing of constant cross section profiles. So profiles have high strength in the length direction, and the principal reinforcements such as glass, carbon, and aramid fibers having 40 to 70% volume, and the matrix materials are used are polyesters, vinyl esters, and epoxy resins. Advantage that it is automated process, it has high speed in production, it is versatile cross sectional shape, and it has continuous reinforcement. Disadvantage is that this dye that is used here, it can be easily messed up, and it is expensive dye, and it has mainly thermoset matrix that can be made using this. So here these are the fibers that are dipped into this resin, then they are pulled using this and extruded according to the required dimensions. Next up is pre-preg. So in this case you have fiber reinforcements which are impregnated with the specific amount of epoxy resin system in a separate step before they lay up. So in this so-called pre-pregging step, fibers are weighted uniformly and a pre-preg of a high quality is formed. The advantages include orientation of fibers, it can be changed, and it is consistent, and it has high productivity. Disadvantages, it is continuous process and needs more customers. It has limited shelf life, and it has problem of delamination. So the process you can see here, epoxy resin is first impregnated with this resin, epoxy resin here, and it is cut into these layups. So these layups then after making these in layup, then you have this preform. So you put in this mold and you keep it covered, then you cure it with heating. After heating, you get the final product. So opening and demolding is next step. These are some of the steps. So preforming, transfer preform into mold, curing and opening and demolding. Last technique, you have resin transfer molding. So in this case, it is also known as the liquid transfer molding process, and it has dry fiber. Dry fiber is preformed into the lower mold and the upper mold is fixed in the place. Then low viscosity resin is injected under some pressure into the mold cavity, where it spreads throughout the fibers. So here are the advantages: design flexibility, low startup cost, faster production, good surface finish. And disadvantages include expensive tooling, time consuming curing and complex mold design. So in this case, you are firstly making a fiber is preformed in this mold. So in this mold you are keeping, and then you are injecting your resin inside this fiber preform, and then after that it is heated so that this thermoset polymer it can set inside this fiber, and then it is ejected and finished part is made. Now that's all from my side. Okay, that's all from my side. as you both joined late, I'll repeat the questions, sample assignment questions once again. So first question is, what is reinforcement in grey cast iron? Your options are cementite flakes, graphite nodules, or cementite spheroids. So in case of grey cast iron, it gets its grey appearance from the graphite flakes. So these are the graphite flakes that are present in microstructure of grey cast iron. So in cast iron and steel, they both act as composites, and graphite and Fe3C, they work as reinforcement in metallic matrix, which can be ferrite or pearlite. Next question is, the continuous phase of a composite materials is known as its disperse phase, reinforcement phase, or matrix phase, or fiber phase. So answer will be matrix phase. So fiber reinforced composites, they look like this one. So here this continuous phase is matrix, which is softer phase, and fibers, they are reinforcement phase. So here answer will be matrix phase. Next question is, which of the following materials are common for whiskers? Whiskers are what? They are single crystals having very small length to diameter ratio. So graphite, silicon carbide, they are used as whiskers. Sorry, they have very large length to diameter ratio, so they have very higher length. So they are in fiber type of, one of the type of fibers. So graphite and silicon carbide, they can be easily made into whiskers. Other are made into either fibers or wires. Next question is Hall-Page relation. In Hall-Page model, hardness increases with a reduction in grain size because grain boundaries act as a source of dislocation, aid dislocation motion, act as barriers to dislocation motion, or act as sinks for dislocation. So dislocation can act as source and sinks for dislocation, but that is not the reason for the strengthening in materials. The strengthening reason is because they act as a barrier to dislocation motion. So C will be the answer. Next is, the below figure depicts the structure of blank composite materials. So this one, you have to tell which type of composite material is this. So options are discontinuous, aligned, laminate, or dispersion strengthened materials. So in this case, you have laminate type of structure because orientation is changing in various layers. So this is laminate type of structure. So a laminar composite is a subcategory type of structural composite with a varying orientation for each layer, and these composite materials are used for their high strength. Next question is, which of the following is correct size range for dispersoids in micrometers and dispersion strengthened composites? Out of these, this B is the answer. So dispersoids in composites are they vary in size from 0.01 to 0.1 micrometer and very small. This size is an important factor for mechanical properties, and fine size dispersoids provide better properties. Next question is, which of the following is not a characteristic trait of composite materials? Options are high strength, toughness modulus, lightweight, easy to assemble, or sensitive to temperature change. Answer will be sensitive to temperature change. So composites are not sensitive to temperature, and other properties are true for the composites. Next is, what type of material is often used in the creation of soft actuators for soft robotics? Options are shape memory alloys, carbon fibers, nylon, and aluminum. So answer will be shape memory alloys. So they convert thermal energy into mechanical energy, making them desirable for making actuators. Next is chain polymerization mechanism may occur due to cationic, anionic, only due to free radical and cationic mechanism, or all of the given options. So D will be the correct answer for this one, because these all are the mechanisms for polymerization. Next question is, which of the following may alter the mechanical properties of reinforced? So options are constituent properties, fiber length, fiber orientation, or all of the mentioned. Answer will be all of the mentioned. So all these reasons, constituent property, fiber length, fiber orientation, etc., they affect overall property of reinforced composites. And here you can see, as you keep on increasing fiber length, your properties such as modulus, strength and impact, they keep on increasing, but processability decreases. Now these are some of the lecture slides which I went through already. So that's all from my side. If you have any query, you can ask.